Hello there, my curious friend. Thank you for joining me once again in this quiet corner of the cosmos, where we let wonder wash over us, like starlight through an open window. Tonight, we're going to embark on perhaps the most ambitious journey imaginable, one that takes us to the very edges of existence itself, and then dares to ask what lies beyond. Picture this: you're standing at the shore of everything that has ever been, will ever be, or could ever be. The waves lapping at your feet aren't made of water, but of space and time themselves. And tonight, we're going to wonder together what it might feel like to take one more step forward into whatever waits beyond the universe itself. Before we begin this cosmic adventure, I'm genuinely curious, where in this vast world are you listening from right now? And what does your clock say at this very moment? Are you tucked under covers as midnight approaches? Or perhaps watching dawn creep across your horizon? If you find yourself soothed by these gentle explorations of the impossible, please consider leaving a like or subscribing, but only if these wandering thoughts truly bring you peace. It helps other restless souls find their way to these quiet contemplations. Now, I must warn you, tonight's topic might be dangerously fascinating. I'm supposed to help you drift off to sleep, but honestly, the question of escaping the universe keeps me awake with wonder sometimes. I'll do my best to keep us floating gently through these cosmic mysteries. So settle in, let your breathing slow, and join me as we venture to the very edge of everything. Imagine you're sitting in a vast, dark theater. The stage before you is illuminated, but beyond the edges of that light, shadows stretch into mystery. This is remarkably similar to our position in the cosmos. We exist within what astronomers call the observable universe, not because it's all there is, but because it's all we can possibly see. The observable universe has a boundary, but not the kind you might imagine. There's no cosmic wall painted with "Do Not Enter" signs, no celestial fence marking where everything ends. Instead, the boundary is created by something far more subtle and profound: the finite speed of light combined with the finite age of our universe. Think of it this way: when you look up at the night sky, you're not seeing the stars as they are now, but as they were when their light began its journey toward your eyes. The nearest star beyond our sun, Proxima Centauri, shows you a version of itself from over 4 years ago. When you gaze at the Andromeda Galaxy, you're seeing it as it appeared over 2 million years in the past. You're literally looking back in time. Now, our universe is approximately 13.8 billion years old. This means that the most distant light we can possibly observe has been traveling toward us for nearly that entire duration. Beyond this cosmic horizon lies, well, we simply don't know, not because we lack the technology, but because the light from those regions hasn't had enough time to reach us yet. It's as if the universe is slowly revealing itself, one photon at a time. The observable universe has a radius of about 46.5 billion light-years. Wait, didn't I just say the universe is only 13.8 billion years old? How can we see things nearly 50 billion light-years away? Here's where it gets wonderfully strange. While that ancient light was traveling toward us, space itself was expanding, stretching the distance between us and the source of that light. The galaxies that emitted the most distant light we can see are now much, much farther away than they were when they sent their messages across the cosmos. Picture yourself trying to walk towards someone on a moving walkway that's carrying you both in opposite directions. Even if you walk steadily forward, the distance between you keeps growing. This is happening throughout the universe. Space itself is expanding, carrying distant galaxies away from us, faster than their light can close the gap. This creates something beautifully poetic. We live inside a sphere of knowability, surrounded by an ocean of mystery. Every day, as the universe ages by 1 day, our observable sphere grows by 1 light day in radius. New photons that have been traveling since the dawn of time finally complete their epic journey and arrive at our telescopes, carrying stories from the deep past. But here's what keeps me staring at the ceiling some nights. This boundary isn't just about what we can see, it's about what we can ever hope to know. Information cannot travel faster than light, so anything happening beyond our cosmic horizon right now is fundamentally unknowable to us. We are cosmic islanders, surrounded by an infinite ocean of mystery. The most distant objects we can observe are sending us light from when the universe was very young, just a few 100 million years old. At that time, the first stars were beginning to shine, and the cosmic dark ages were ending. Beyond that visible horizon, there might be countless galaxies, civilizations, wonders, and worlds. Or there might be something completely different, regions where the laws of physics operate in ways we can't imagine. Standing at the edge of our observable universe is like being a child with your face pressed against a frosted window. You can see shapes and shadows, hints of something vast beyond, but the details remain tantalizing mysteries. Every photon that reaches us is a messenger from the deep past, carrying news from the frontier of the knowable. And each message reminds us that for all our cosmic knowledge, we are still just beginning to understand the true scope of existence. Now, let's venture into even deeper waters, where the distinction between what we can see and what actually exists becomes as mysterious as morning mist. The observable universe, a cosmic neighborhood of visibility, might be just a tiny droplet in an ocean so vast that it makes our grandest cosmic measurements seem like counting grains of sand on an infinite beach. Consider this humbling thought. If the entire observable universe, with all its hundreds of billions of galaxies, was shrunk down to the size of a marble, the actual universe might still be larger than Earth, or perhaps larger than our solar system, or maybe even infinite. We honestly don't know, and that uncertainty is both thrilling and vertigo-inducing. The actual universe, the totality of everything that exists, extends far beyond our cosmic horizon. While we can observe galaxies nearly 46.5 billion light-years away, the whole universe might stretch for hundreds of billions, or trillions, or even infinite light-years in every direction. Imagine standing in the middle of a vast forest at night, with only a small flashlight. The circle of trees you can illuminate represents your observable universe, but the forest itself might extend endlessly into the darkness. What makes this even more fascinating is that different regions of the actual universe have their own observable bubbles. Right now, somewhere unimaginably far away, there might be other beings looking up at their night sky, seeing a completely different collection of galaxies and stars. Their observable universe barely overlaps with ours, or perhaps doesn't overlap at all. We are cosmic strangers, separated not just by distance, but by the fundamental limits of information and light. This leads to a beautiful paradox. There are regions of our own universe that we will never be able to see, not because they're too far away now, but because they're moving away from us too quickly. The expansion of space is accelerating, driven by the mysterious dark energy that permeates all of existence. Eventually, distant galaxies will be carried away from us faster than their light can travel toward us. They will fade from view, one by one, until future observers see a much lonelier cosmos. But here's where the story becomes truly strange. In those unreachable regions of the actual universe, the same physical laws likely apply. The same types of stars shine, planets form, and perhaps life evolves. There might be worlds with purple sunsets, civilizations that have solved mysteries we haven't even discovered yet, or forms of beauty that would take our breath away. All of this exists, or probably exists, but remains forever beyond our reach. Some cosmologists propose that if you could travel far enough through the actual universe, you might eventually encounter regions that look exactly like our own cosmic neighborhood. In an infinite universe with finite ways for matter and energy to arrange themselves, every possible configuration must repeat eventually. This means there might be countless versions of Earth, countless versions of you, living lives that are nearly identical or completely different. The mathematics of infinity suggests something even more mind-bending. If the universe is truly infinite, then not only does everything that's possible happen somewhere, but it happens infinitely many times. There are infinite versions of you reading these words right now, and infinite versions experiencing slight variations of this exact moment. Yet we remain trapped in our small, observable bubble, like deep-sea creatures who can only see as far as their bioluminescence reaches. The actual universe surrounds us with its vastness, but we can only ever experience this tiny local sample of reality. It's as if we're trying to understand an entire library by reading just one page of one book. This separation between the observable and the actual creates a profound sense of cosmic loneliness. Somewhere out there, beyond the edge of what we can ever see, incredible things are happening right now. Stars are being born in stellar nurseries we'll never glimpse. Planets are forming that will never appear in our telescopes. Perhaps other conscious beings are looking up at their skies and wondering, just as we are, what lies beyond their own cosmic horizon. The actual universe keeps its secrets well. It surrounds us with mysteries that no amount of technological advancement can fully unveil. We are like children peering through a keyhole at a vast mansion, catching glimpses of wonders we can barely comprehend, while knowing that entire wings of reality remain forever hidden from view. And perhaps that's exactly as it should be. The universe has given us just enough visibility to inspire wonder, but kept enough mystery to ensure that our sense of awe never fades. Let's pause here and consider one of the universe's most fundamental rules, a cosmic speed limit that governs not just how fast things can move, but how quickly information, causality, and even knowledge itself can spread through reality. The speed of light isn't just fast. It's the maximum speed at which cause and effect can propagate through the fabric of space and time. Imagine the universe as a vast postal system, where every piece of information must be delivered by messengers traveling at exactly the same speed. No faster, no slower. These messengers are photons, particles of light, and they travel at approximately 300,000 kilometers per second. This might seem impossibly fast, and it is by earthly standards, but in the context of cosmic distances, light moves with what feels like cosmic molasses. When you flip a light switch, the illumination appears instantaneous because your room is so small that light crosses it in mere nanoseconds. But scale this up to cosmic proportions, and the delays become profound. The light from our sun takes over 8 minutes to reach Earth. If the sun suddenly vanished, we wouldn't know for 8 minutes. We'd continue basking in sunlight that was already on its way, like reading a letter from someone who has already left town. This speed limit creates something philosophers and physicists call light cones, geometric representations of what can influence what and when. Picture dropping a pebble into a perfectly still pond. The ripples spread outward at a constant speed, and nothing inside the expanding circle of ripples can be affected by anything outside it until the ripples reach them. Similarly, every event in the universe creates expanding spheres of influence, limited by the speed of light. This fundamental constraint shapes our cosmic isolation in ways both beautiful and melancholy. When you look at a star 10,000 light-years away, you're seeing it as it was 10,000 years ago. If that star exploded yesterday, you won't know for 10,000 years. If civilizations exist around that star, and they're looking back at us, they're seeing Earth as it was 10,000 years ago. A world of hunter-gatherers, unaware that someday their descendants would build telescopes and wonder about distant stars. The speed of light also explains why escaping the universe, if such a thing were even possible, would be such a profound challenge. Information about what lies beyond our cosmic horizon hasn't had time to reach us yet. But more than that, even if we could somehow travel at light speed, we could never outrun the expanding boundary of our observable universe. We would be like runners on a cosmic treadmill, where the finish line moves away from us as quickly as we approach it. Einstein showed us that the speed of light isn't just about light, it's about the structure of space and time themselves. As objects approach light speed, time slows down for them relative to the rest of the universe. At light speed itself, time would stop entirely. This creates a beautiful impossibility to truly escape the universe by outrunning the expansion of space. You would need to travel faster than light, but doing so would require infinite energy and would break the fundamental structure of causality itself. But here's where the story becomes wonderfully strange. While nothing can travel through space faster than light, space itself has no such restriction. During the first fraction of a second after the Big Bang, space expanded much faster than light speed. which is why we can now see objects that are much farther away than light could have traveled in the age of the universe. Space can stretch and carry objects away from each other faster than light, but the objects themselves aren't breaking the speed limit. They're passengers on the expanding fabric of reality. This creates our cosmic prison, but it's a prison made of the most fundamental laws of physics. We cannot escape to see what lies beyond, because the very structure of space and time prevents us from doing so. Yet this limitation also creates something beautiful. It means that every photon reaching us has undertaken an epic journey, carrying information across vast distances and eons of time. Every time you look up at the night sky, you're receiving messages that have traveled for years, centuries, millennia, or even billions of years to reach your eyes. You are in that moment participating in a cosmic conversation that spans unimaginable distances and timescales. The speed of light might limit our ability to explore beyond our cosmic horizon, but it also connects us to the deep past and the far reaches of observable space. So we remain here, in our expanding bubble of visibility, receiving ancient light from distant worlds, forever wondering what lies beyond the cosmic horizon that retreats from us at the speed of causality itself. Close your eyes for a moment and imagine you're inside a balloon that's being gently inflated. But this isn't an ordinary balloon. It's a balloon where you, and everything you've ever known, are patterns drawn on the rubber surface itself. As the balloon expands, the distance between every point on its surface grows larger, not because anything is moving through the rubber, but because the rubber itself is stretching. This is remarkably similar to what's happening to our universe right now, at this very moment, as you listen to these words. Space itself is expanding, carrying galaxies away from each other like raisins in rising bread dough. But unlike the raisins, which are separate objects embedded in the dough, galaxies are part of the fabric of space-time itself, passengers on an expanding cosmic ocean. The discovery of cosmic expansion was one of the most revolutionary moments in human understanding. In the 1920s, astronomer Edwin Hubble noticed something peculiar when he observed distant galaxies. Their light was shifted toward the red end of the spectrum, what we call redshift, and the more distant a galaxy was, the more its light was reddened. This wasn't because the galaxies were moving away from us through space, but because the space between us and them was stretching, literally stretching the wavelengths of light as they traveled across the cosmos. Think of this stretching like a sound you might hear from a train passing in the night. As the train approaches, its whistle sounds higher in pitch, and as it moves away, the pitch drops lower. But cosmic redshift is different. It's as if the air itself were expanding, changing the pitch of the whistle, not because the train is moving, but because the medium carrying the sound is growing larger. This expansion happens everywhere, at every scale, but we don't notice it in our daily lives, because the effect is incredibly subtle over small distances. The space between your hands isn't expanding fast enough to measure, nor is the space between Earth and the Sun. Even the distance between our galaxy and our nearest galactic neighbor, Andromeda, isn't increasing because gravity holds us together in what astronomers call gravitationally bound systems. It's only at the largest scales, between galaxy clusters, separated by hundreds of millions of light-years, that the expansion becomes significant. The rate of this expansion is described by something called the Hubble constant, though constant is a bit of a misnomer since it changes over cosmic time. Right now, space is expanding at a rate of about 70 kilometers per second per megaparsec. This means that for every 3.26 million light-years of distance, space is stretching at an additional 70 kilometers per second. It sounds fast, but it's actually quite gentle, about the speed of a car on a highway, spread across distances so vast they boggle the mind. What makes this expansion truly mind-bending is that it's happening everywhere simultaneously. There's no center to the expansion, no special point from which everything is moving away. Every galaxy sees every other distant galaxy moving away from it, just as every point on the surface of our inflating balloon sees every other point moving away. We are not at the center of the universe. Rather, every point in the universe appears to be at the center of the expansion from its own perspective. This creates what cosmologists call the cosmological principle, the idea that the universe looks roughly the same in all directions and from all locations, at least on the largest scales. It's a democratically expanding cosmos, where no location holds a privileged position. Your cosmic neighborhood and a galaxy billions of light-years away are both experiencing the same expansion, the same gentle stretching of space itself. The expansion also means that the universe is becoming less dense over time. As space grows larger, the same amount of matter and energy gets spread over an increasingly vast volume. Galaxies don't grow larger during this expansion. They're held together by gravity, but the emptiness between them grows ever more empty, ever more vast. This leads to a profound realization. If we could run time backward, we would see the universe contracting, becoming denser and hotter, until we reach a point where all the space we can observe was compressed into a region smaller than an atom. This is the Big Bang, not an explosion in space, but the expansion of space itself from an unimaginably small and dense state. The expansion of the universe means that we're living in a cosmos that's constantly changing, constantly growing, constantly becoming something new. Every second, space grows a little larger, carrying distant galaxies a little farther away, making the universe a little more vast and a little more mysterious. We are passengers on an expanding ship sailing through an ocean of space-time, and our destination is an ever more spacious cosmos, where the distances between islands of matter grow ever greater. Now we encounter one of the universe's deepest mysteries, something so strange and counterintuitive that it challenges our most basic assumptions about how reality should behave. For decades after discovering that the universe was expanding, scientists assumed this expansion would gradually slow down over time. After all, gravity should be pulling everything back together, acting like a cosmic brake on the expansion. But in the late 1990s, astronomers made a discovery that shook cosmology to its core. The expansion of the universe is not slowing down, it's speeding up. Imagine throwing a ball into the air and watching it not just continue upward but actually accelerate as it rises, flying faster and faster away from you. This would violate everything you know about gravity and physics. Yet this is essentially what we've discovered about our universe. Not only is space expanding, but the rate of expansion is increasing with each passing moment. This acceleration is driven by something we call dark energy, though the name reveals our profound ignorance about what it actually is. We call it dark, not because it absorbs light, but because it's invisible to all our instruments except for its gravitational effects. We call it energy because it seems to fill space with a kind of anti-gravitational pressure. But honestly, dark energy might be the most poorly understood phenomenon in all of science. Here's what makes dark energy so mysterious. It appears to be a property of space itself. As the universe expands and creates more space, there's more dark energy. It's as if empty space has an intrinsic energy density that remains constant even as space grows larger. Here's what makes dark energy so mysterious. It appears to be a property of space itself. As the universe expands and creates more space, there's more dark energy CDFR. This creates a runaway effect. More space means more dark energy, which causes faster expansion, which creates even more space, and so on. Think of it like this. Imagine a soap bubble that instead of popping or staying the same size, actually becomes more energetic as it grows larger. The bigger it gets, the faster it expands. And the faster it expands, the bigger it gets. This is what's happening to our universe on the grandest possible scale. Dark energy makes up about 68% of all the energy in the universe. Dark matter, another mysterious component, accounts for about 27%. This means that ordinary matter, everything we can see, touch, and understand, makes up less than 5% of reality. We are living in a universe dominated by phenomena we cannot directly observe and do not understand. It's humbling and exhilarating at the same time. The implications of accelerating expansion are profound and somewhat melancholy. As dark energy continues to drive galaxies apart, the universe is entering what cosmologists call the age of isolation. Eventually, galaxies will be carried so far apart by the expansion of space that light from one will never be able to reach another. Each galaxy will become a cosmic island, alone in an ever-expanding ocean of darkness. Far in the future, Trillions of years from now, beings living in any galaxy will look up at their night sky and see nothing. No other galaxies, no cosmic microwave background, no evidence that there was ever a Big Bang, or that the universe was once small and dense. They will inhabit what appears to be a small, isolated island of stars in an infinite, empty void. The cosmic evidence for the Big Bang, for the expansion of space, for the deep connection between all matter and energy, will have been literally carried beyond their cosmic horizon. This makes us incredibly fortunate to be living now in what we might call the golden age of cosmology. We can still see the afterglow of the Big Bang, still observe distant galaxies, still piece together the story of cosmic evolution. We are perhaps the first generation of humans to understand our cosmic context, and we may be among the last beings in the universe's history to have access to the evidence that reveals this context. But dark energy might hold even stranger surprises. Some theories suggest that its strength could change over time, or that it might eventually reverse, causing the expansion to slow down and even reverse into a big crunch. Other theories propose that dark energy could grow so strong that it eventually rips apart not just galaxies, but solar systems, planets, atoms, and even space-time itself, in what's called the Big Rip. For now, dark energy remains one of the universe's greatest puzzles. It surrounds us, fills the space between atoms, and drives the cosmic expansion that will ultimately determine the fate of everything that exists. Yet we understand it about as well as ancient peoples understood the wind. We can see its effects, feel its presence, but its true nature remains tantalizingly out of reach. We live in a universe where the vast majority of reality consists of invisible forces and substances that we're only beginning to comprehend. Dark energy reminds us that for all our scientific advances, we are still cosmic children, just beginning to explore the deepest mysteries of existence. Let's pause here and really contemplate what we mean when we say that space itself is expanding, because this concept is so fundamentally strange that it challenges our most basic intuitions about reality. We're not talking about objects moving through space. We're talking about space itself growing larger, creating new distance where none existed before. Imagine you're an ant walking on the surface of a balloon. From your tiny perspective, the balloon's surface is your entire universe, a two-dimensional world that contains everything you've ever known. Now, as someone inflates the balloon, what happens? The surface doesn't just get bigger. New surface area literally comes into existence. The distance between any 2 points on the balloon increases, not because those points are moving through the surface, but because there's simply more surface between them than there was before. This is analogous to what's happening in our three-dimensional space, except we need to think in 4 dimensions to truly understand it. Our universe is like the three-dimensional surface of a 4-dimensional balloon that's being inflated. New space is constantly being created between existing points, making the universe larger without anything actually moving through space in the traditional sense. This expansion of space creates some wonderfully counterintuitive effects. Consider 2 galaxies that are sufficiently far apart. As space expands between them, they can move away from each other faster than the speed of light, without violating Einstein's prohibition against faster-than-light travel. They're not moving through space at light speed. They're being carried apart by the creation of new space itself. It's like standing on 2 conveyor belts moving in opposite directions. You can separate faster than you could run, even though you're not running at all. The expansion of space also explains why the cosmic microwave background radiation, the afterglow of the Big Bang, appears to come from all directions. When this radiation was first emitted, about 380,000 years after the Big Bang, the universe was much smaller and much denser. The light from that era has been stretched by the expansion of space itself, turning what was once visible light into microwaves that we can detect today. Every cubic centimeter of space around you is filled with these ancient photons, stretched by billions of years of cosmic expansion. Here's something that might keep you awake tonight, right now, as you listen to these words. Space is expanding between you and everything around you. The expansion is incredibly slow at small scales. The distance between you and your pillow isn't measurably increasing. but it's happening nonetheless. At larger scales, between galaxy clusters, new kilometers of empty space are literally materializing every second. This expansion also means that the concept of distance in the universe is more complex than it first appears. When we say a galaxy is 10 billion light-years away, we need to specify what we mean. Is that how far away it was when the light we're seeing left it? How far away it is now? How far away it would be if we could somehow travel there instantly? Each of these distances is different because space has been expanding throughout the journey of the light. The expansion of space creates something called the particle horizon, a boundary beyond which we cannot see, not because there's nothing there, but because light from those regions hasn't had time to reach us yet. But more intriguingly, it also creates what's called the event horizon, a boundary beyond which we will never be able to see, no matter how long we wait, because space is expanding faster than light can travel across it. Think about this. There are galaxies out there whose light is traveling toward us right now. But because space is expanding, that light will never reach us. It's like trying to swim upstream in a river that flows faster than you can swim. These galaxies are forever beyond our reach, not because they're too far away, but because new space is being created between us and them faster than light can cross it. The expansion of space also raises profound questions about the nature of existence itself. If space is expanding, what is it expanding into? The answer, according to our best understanding, is that this question doesn't make sense. Space isn't expanding into anything. There is no outside space for it to expand into. Space is simply becoming larger, creating more of itself as it goes. This might be the most mind-bending aspect of cosmic expansion. The universe doesn't need a container. It doesn't need to expand into some pre-existing void. It creates its own room to grow, generating new space from within itself through processes we can observe but barely comprehend. We live in a reality that is literally making itself larger moment by moment, creating new possibilities for existence with each passing second. The expansion of space means we inhabit a universe that is fundamentally creative, constantly bringing new distances, new volumes, new possibilities into being. It's a cosmos that grows not just in size, but in potential, an ever-expanding stage for the cosmic drama of matter, energy, and perhaps consciousness itself. Imagine holding a photograph of yourself as a baby, the earliest picture ever taken of you, capturing a moment when you were so young that you barely resembled who you are today. Now imagine that this photograph wasn't taken with a camera, but was written in light itself, and that you could still see this ancient image by simply knowing where to look. This is essentially what we have with the cosmic microwave background radiation, a baby picture of the entire universe, frozen in light that has been traveling toward us for nearly 13.8 billion years. The cosmic microwave background, or CMB as astronomers fondly call it, represents the moment when the universe first became transparent to light. Before this moment, roughly 380,000 years after the Big Bang, the universe was so hot and dense that electrons and protons couldn't combine to form atoms. Free electrons scattered photons constantly, making the universe opaque, like trying to see through a thick fog. But as the universe expanded and cooled, it reached a temperature where electrons could finally bind to protons, creating hydrogen atoms and clearing the cosmic fog. At that moment, which cosmologists call recombination, the universe became transparent for the first time. Light that had been trapped in the hot, dense plasma could finally travel freely through space. This light has been journeying toward us ever since, carrying with it the image of what the universe looked like when it was just a cosmic infant, barely 0.003% of its current age. What makes this even more remarkable is that this ancient light surrounds us completely. Every cubic centimeter of space, including the space between your atoms, is bathed in photons from the cosmic microwave background. When early radio astronomers first detected this radiation in 1965, they initially thought it was just noise from pigeon droppings on their antenna. They had no idea they were listening to the echo of creation itself. The CMB appears to us now as microwave radiation, with a temperature of about 2.7 degrees above absolute zero. This is incredibly cold, but it was once the visible light of a universe heated to thousands of degrees. The expansion of space has stretched these ancient photons, shifting them from visible light through infrared and into the microwave portion of the electromagnetic spectrum. It's as if the universe's baby picture has been printed on a piece of paper that's been stretched so much that the image has become nearly invisible to our eyes. When scientists map the cosmic microwave background across the entire sky, they see something breathtakingly beautiful, a nearly uniform glow with incredibly tiny variations, hot spots and cold spots that differ in temperature by mere millionths of a degree. These minute fluctuations represent the seeds of everything we see in the universe today. All regions that were slightly denser than average would eventually grow through gravitational attraction to become the clusters of galaxies we observe today. Areas that were slightly less dense would become the vast cosmic voids between them. In a very real sense, when you look at a map of the cosmic microwave background, you're seeing the blueprint for all of cosmic structure. Those tiny temperature variations, imprinted when the universe was smoother than anything we can imagine today, contain the genetic code for every galaxy, every star, every planet, and perhaps every life form that would ever exist. The precision with which we can measure the CMB is almost magical. We can detect temperature variations so small that if you heated a cup of coffee by that amount, the change would be smaller than the thickness of a human hair compared to the height of a skyscraper. Yet these infinitesimal differences tell us about the fundamental properties of the universe, its age, its composition, its geometry, and its ultimate fate. What's particularly enchanting about the cosmic microwave background is that it represents the last moment of cosmic simplicity. Before recombination, the universe was relatively uniform and predictable. After recombination, gravity began sculpting matter into the complex structures we see today: stars, galaxies, planets, and eventually consciousness itself. The CMB is the dividing line between cosmic simplicity and cosmic complexity, between a universe of smooth plasma and a universe capable of creating beings who can contemplate their own origins. When you step outside on a clear night and look up at the stars, remember that your eyes are not just seeing the light from distant suns. Mixed in with that starlight, invisible to your vision, but detectable by sensitive instruments, are the most ancient photons in the universe. Light that began its journey when the cosmos was young and unmarked by time, carrying within it the story of how everything you see came to be. The cosmic microwave background is perhaps the most profound baby picture ever taken, showing us not just what the universe looked like in its infancy, but revealing the subtle patterns that would eventually give rise to all the beauty and complexity we observe today. The cosmic microwave background creates something that sounds like it belongs in a science fiction story, wholly an impenetrable wall that surrounds us completely, beyond which we cannot see. It's no matter how powerful our telescopes become. But this isn't a wall made of matter or energy in any conventional sense. It's a wall made of opacity itself, a boundary between the knowable and the unknowable past. Picture yourself in a vast library where every book contains the history of the universe, but someone has placed a one-way mirror at a certain shelf. You can see your reflection in the mirror and everything on your side of it, but you cannot see beyond it to the older books that rest in the deeper archives. The cosmic microwave background is like that mirror. It reflects the image of the universe at a specific moment in time, but prevents us from seeing any deeper into the past. Before the moment of recombination, when the cosmic microwave background was created, the universe was opaque to electromagnetic radiation. Photons couldn't travel very far before colliding with free electrons, scattering in random directions like light trying to penetrate a thick fog. No telescope, no matter how sensitive, can peer through this cosmic fog to see what lay beyond. It's not a limitation of our technology, it's a fundamental property of the universe itself during that era. This creates a profound boundary in our cosmic knowledge. We can see galaxies that formed hundreds of millions of years after the Big Bang, and we can detect the cosmic microwave background from when the universe was 380,000 years old. But the era between the Big Bang and recombination, those first 380,000 years, remains largely hidden from direct optical observation. It's like having a detailed photo album of someone's life starting from age 5, but having no pictures from their early childhood. Yet this wall is not completely impermeable. While electromagnetic radiation cannot penetrate the pre-recombination universe, other messengers might be able to carry information from those hidden eras. Gravitational waves, ripples in spacetime itself, can travel through matter without scattering. If we could detect gravitational waves from the early universe, and this is an active area of research, we might be able to peer beyond the cosmic microwave background wall and glimpse the universe in its first moments. Neutrinos, those ghostly particles that barely interact with matter, also created their own version of a cosmic background when the universe was just 1 second old. The cosmic neutrino background exists, surrounding us just as the cosmic microwave background does, but it's incredibly difficult to detect. If we could map these primordial neutrinos, we would have a window into the universe when it was unimaginably young and dense. Davitis, Winterdifel Egio Sidapeva. The cosmic microwave background wall also represents a boundary between two completely different phases of cosmic evolution. On our side of the wall, we see a universe of structure and complexity, galaxies, stars, planets, and the rich chemistry that makes life possible. But beyond the wall lies a universe of primordial simplicity, where matter existed only as an hot, dense plasma of fundamental particles. This wall moves with us as we look deeper into space and further back in time. No matter which direction we look, we eventually encounter this boundary at roughly the same distance from us. It surrounds us like a spherical screen onto which the image of the young universe is projected. We sit at the center of this cosmic theater, watching the earliest possible show, but always aware that the real action, the universe's birth itself, remains forever behind the curtain. What makes this boundary particularly fascinating is that it's not fixed in space. It's a moving boundary in time. Every day, as the universe ages by 1 day, the cosmic microwave background that we see today becomes slightly older, and the wall moves an infinitesimal amount further back in time, but we can never catch up to it, never see beyond it, because the opacity of the early universe ensures that no electromagnetic information from before recombination can ever reach us. The existence of this wall also highlights something beautiful about the nature of cosmic observation. We are fundamentally time travelers, looking into the past every time we observe the universe. The CMB wall represents the ultimate destination of this time travel, all the furthest back we can see using light itself. Beyond this wall, the universe's infancy remains cloaked in mystery, accessible only through theoretical physics and indirect observations. In a strange way, the cosmic microwave background wall makes us appreciate the transparency of the modern universe. The fact that we can see stars, galaxies, and distant quasars is not a given. It's a consequence of the universe having cooled enough for atoms to form and for space to become clear. We live in a transparent cosmos, but we are surrounded by the image of a time when the universe was fundamentally different, fundamentally opaque, fundamentally unknowable through direct observation. This wall reminds us that even our most powerful tools of discovery have limits, and that some mysteries may remain forever beyond our direct reach, hidden behind barriers that are written into the very structure of space and time. When scientists first created detailed maps of the cosmic microwave background, they discovered something that would change our understanding of the universe forever. The ancient light wasn't perfectly uniform. Instead, it contained incredibly subtle patterns, tiny variations in temperature, all that represented the seeds of everything we see in the cosmos today. These patterns tell a story so profound that it's like finding the sheet music from which all of cosmic history has been composed. Imagine looking at a perfectly calm lake at dawn, so still that it appears like a mirror. But as you look more carefully, you notice the tiniest ripples on the surface, variations so small, they're barely perceptible. Yet these minute disturbances contain the potential to become waves that will eventually reshape the entire shoreline. The temperature variations in the cosmic microwave background are like those primordial ripples, containing within them the blueprint for all cosmic structure. These temperature differences are almost impossibly small. We're talking about variations of just a few millionths of a degree. If the cosmic microwave background had an average temperature of room temperature instead of nearly absolute zero, these variations would be smaller than the difference between a perfect summer day and that same day with a single snowflake added to the atmosphere. Yet from these infinitesimal differences, all the complexity and beauty of the modern universe would eventually emerge. The patterns we see in the CMB represent quantum fluctuations that were stretched to cosmic proportions during the first moments after the Big Bang. In the very early universe, even empty space was subject to quantum uncertainty, tiny fluctuations in energy density that normally occur at subatomic scales. But during a period called cosmic inflation, these microscopic variations were amplified and stretched across regions that would eventually become larger than galaxy clusters. Think of it like this. Imagine writing a message with the finest pen possible, so fine that the letters are smaller than atoms. Then imagine photocopying that message billions and billions of times, each copy slightly larger than the last, until the letters become visible to the naked eye. This is similar to what happened to quantum fluctuations during cosmic inflation. Tiny variations in the very fabric of space-time were amplified until they became the large-scale structures we observe today. The specific patterns in the cosmic microwave background contain an astonishing amount of information about the fundamental properties of our universe. By analyzing these patterns, scientists have been able to determine the universe's age, 13.8 billion years, its composition, about 5% ordinary matter, 27% dark matter, and 68% dark energy, and even its geometry, remarkably close to perfectly flat. It's as if the universe left us a detailed recipe card, written in the language of temperature variations across the sky. One of the most beautiful aspects of these patterns is how they reveal the acoustic oscillations of the early universe. Before recombination, the universe was filled with a hot plasma that could support sound waves, pressure waves, that propagated through the cosmic fluid like ripples through water. These primordial sound waves created regions of compression and rarefaction in the plasma, and when recombination occurred, these acoustic patterns were frozen into the cosmic microwave background like a snapshot of cosmic music. The scale of these acoustic oscillations tells us about the size of the universe at the time of recombination, which in turn reveals fundamental constants of physics and cosmology. The largest temperature variations in the CMB correspond to regions that were about 1 degree across in the sky, coincidentally, about twice the apparent size of the full moon. This scale represents the farthest distance that sound waves could have traveled in the 380,000 years between the Big Bang and recombination. What makes these patterns even more remarkable is their implications for the future. The slightly denser regions that appear as warm spots in the cosmic microwave background were destined to become the locations where the first stars would form, where galaxies would cluster, and where the complex chemistry necessary for life would eventually emerge. In a very real sense, the patterns in the CMB predicted the existence of the Milky Way, our solar system, and ultimately, the cosmic microwave background patterns also provide evidence for cosmic inflation, the idea that the universe underwent a period of exponential expansion in its first moments. The remarkable uniformity of the CMB across the entire sky, interrupted only by these tiny variations, suggests that regions of the universe that could never have been in contact with each other somehow share the same temperature and properties. Inflation explains this by proposing that these apparently disconnected regions were once close together before being stretched apart by the expansion of space itself. Perhaps most wonderfully, these patterns represent the earliest evidence of causality in our universe, the subtle imprint of cause and effect operating on cosmic scales. Every warm spot and cool spot in the cosmic microwave background had consequences that rippled forward through billions of years of cosmic evolution, ultimately contributing to the universe's ability to create stars, planets, and conscious beings capable of contemplating their own origins. When we look at the patterns in the cosmic microwave background, we're seeing the universe's first draft of the future. written in the language of temperature and density, telling the story of how simplicity gradually gave way to all the complexity and wonder we observe today. Let's embark on a thought experiment that pushes the boundaries of physics and imagination. We're familiar with the concept of escape velocity from everyday objects. Throw a ball upward at 11.2 kilometers per second, and it will escape Earth's gravitational pull forever, sailing off into space without ever falling back down. Let's embark on a thought experiment that pushes the boundaries of physics and imagination. But what would it mean to achieve escape velocity from the universe itself? What would it take to break free from the ultimate gravitational embrace of all existence? The question immediately runs into fundamental problems that make it both fascinating and seemingly impossible. Unlike escaping from a planet or even a galaxy, escaping from the universe confronts us with the problem of defining what outside the universe even means. If the universe contains all of space and time, then the concept of escaping it becomes as paradoxical as asking what's north of the North Pole. But let's push forward with our cosmic thought experiment anyway. In classical mechanics, escape velocity depends on mass and radius. The more massive an object, and the more concentrated its mass, the higher the escape velocity. For Earth, it's about 11 kilometers per second. Hall, Faucher, it's about 11 kilometers per second. For the Sun, it's over 600 kilometers per second. For a black hole, escape velocity at the event horizon equals the speed of light itself, which is why not even light can escape once it crosses that boundary. Now, what about the observable universe? If we treat it as a massive sphere containing all the matter and energy we can see, we can calculate its escape velocity. The observable universe contains perhaps 10 circumflex 53 kilograms of matter and energy spread across a region about 93 billion light-years in diameter. When you plug these numbers into the escape velocity equation, something remarkable happens. The escape velocity from the observable universe turns out to be very close to the speed of light. This is not a coincidence. It's a profound hint about the relationship between the size of our cosmic horizon and the fundamental constants of physics. We live in a universe where the escape velocity from the observable region approaches the ultimate speed limit of reality itself. It's as if the universe is balanced right at the edge between expansion and gravitational collapse, between openness and closure. But here's where the physics becomes truly mind-bending. Even if you could somehow accelerate a particle to near light speed in an attempt to escape the universe, the expansion of space itself would work against you. As space expands, it carries distant regions away from you faster than you could possibly travel toward them. You would be like a swimmer trying to reach the far shore of a river, but the river keeps getting wider faster than you can swim. The cosmic escape velocity problem also runs headfirst into Einstein's theory of relativity. As any object approaches the speed of light, its mass effectively becomes infinite, requiring infinite energy to accelerate it further. This creates an unbreachable barrier to escape the universe's gravitational pull. You would need to travel at or near light speed, but the laws of physics prohibit any massive object from actually reaching that speed. Even more fundamentally, the very concept of escaping the universe assumes that there's somewhere to escape to. But if space-time itself is a property of the universe, then outside the universe may not be a meaningful location. It's like asking how to step outside of existence itself. The question may be grammatically correct, but physically meaningless. Yet there are theoretical scenarios where something like cosmic escape might be possible. Some interpretations of quantum mechanics suggest that information, if not matter, might be able to transcend the boundaries of our cosmic region through quantum entanglement or other non-local effects. In the many worlds interpretation of quantum mechanics, every quantum event creates parallel universes, suggesting that parts of reality might constantly be escaping into other branches of the cosmic tree. String theory and other advanced physics theories propose the existence of extra dimensions beyond the three spatial dimensions we experience. If these theories are correct, then escaping our universe might not mean traveling faster than light through our familiar three-dimensional space, but rather finding a way to move through higher dimensional space that connects our universe to others. The concept of cosmic escape velocity also raises profound questions about the nature of physical laws themselves. Are the speed of light, the strength of gravity, and the structure of space-time universal constants, or are they local properties of our particular cosmic region? If we could somehow escape to another universe, would physics work differently there? Perhaps most intriguingly, the impossibility of achieving cosmic escape velocity might itself be a feature, not a bug, of reality. If it were easy to escape from universes, cosmic evolution might not have had the time and stability necessary to create complexity, chemistry, and consciousness. The fact that we appear to be trapped within our cosmic horizon might be precisely what allowed the universe to become interesting enough to produce beings capable of contemplating cosmic escape in the first place. In the end, the concept of cosmic escape velocity leads us to one of the deepest questions in physics and philosophy. What are the ultimate boundaries of existence, and what might lie beyond them? The universe seems to have conspired against any possibility of escape, weaving together gravity, space, and time into an intricate cosmic web that becomes more constraining the more we understand it. It's as if reality itself is designed to be a closed system, a cosmic hotel where you can check in, but you can never truly check out. Let's explore how these fundamental forces work together to create what might be the ultimate prison, one made not of bars or walls, but of the very structure of existence itself. Gravity, that most familiar of forces, reveals its true nature only when we consider it on cosmic scales. What we experience as the gentle pull that keeps our feet on the ground is actually the curvature of space-time itself, bent by the presence of mass and energy. Every particle of matter in the universe contributes to this curvature, creating a vast four-dimensional landscape of hills and valleys through which everything must travel. Imagine space-time as a vast rubber sheet stretched tight, with every star, planet, and galaxy creating dimples and depressions in the fabric. Now imagine trying to roll a marble fast enough that it escapes from this sheet entirely. Where would it go? The sheet itself represents all of space. There is no off the sheet for the marble to escape to. This is the predicament we face when contemplating escape from the universe. We're trying to leave a system that defines the very concept of place itself. As we've seen, the expansion of space adds another layer of complexity to our cosmic imprisonment. Space itself is growing, carrying distant regions away from us at ever-increasing speeds. But this expansion isn't uniform throughout the universe. It's strongest at the largest scales, between galaxy clusters, while being essentially negligible within gravitationally bound systems like our local galaxy group. This creates a kind of cosmic hierarchy of escape. You could, in principle, escape from Earth's gravity well with enough energy. You could even escape from our solar system or our galaxy, given sufficient velocity. But as you try to escape to larger and larger scales, the expansion of space itself begins to work against you. The very distances you're trying to traverse are growing larger even as you attempt to cross them. Time adds the final twist to this cosmic conspiracy. Einstein showed us that space and time are not separate entities, but aspects of a single, unified space-time. As you approach the speed of light in your attempt to escape the universe, time dilation effects become extreme. From your perspective, time would slow to a crawl, while the rest of the universe ages rapidly around you. The universe you're trying to escape would evolve and change, while you remain frozen in slow motion. But perhaps most importantly, the finite age of the universe creates what cosmologists call a particle horizon, a fundamental limit to how far we can see or travel. Light from the most distant observable objects has been traveling toward us for nearly 13.8 billion years. Beyond this horizon lies a region of space that is not just practically unreachable, but theoretically unknowable. You cannot escape to a place that doesn't yet exist in your causal future. The conspiracy deepens when we consider dark energy, that mysterious force driving the accelerated expansion of space. Dark energy acts like a kind of anti-gravity on cosmic scales, but instead of helping objects escape from the universe, it actually makes escape more difficult by increasing the rate at which distant regions recede from us. It's as if the universe is not just a prison, but a prison that's actively making itself larger to ensure that escape becomes more impossible with each passing moment. Even more subtly, the fundamental constants of physics seem fine-tuned in a way that makes cosmic escape impossible. If gravity was slightly weaker, matter wouldn't clump together to form stars and planets. If the speed of light were higher, the cosmic horizons would be different, potentially allowing more cosmic communication, but also making the universe's evolution proceed differently. The precise values of these constants create a universe that is stable enough for complexity to emerge, but constrained enough to prevent escape. Quantum mechanics adds yet another layer to this conspiracy. The uncertainty principle tells us that you cannot simultaneously know both the position and momentum of a particle with perfect precision. On cosmic scales, this translates to fundamental limits on how precisely you can navigate through space-time. Even if escape were theoretically possible, quantum uncertainties might prevent you from executing the precisely calibrated trajectory necessary to achieve it. The three-dimensional topology of space itself might be the final conspirator. If space curves back on itself, if the universe is shaped like a hypersphere or some other closed manifold, then traveling far enough in any direction might eventually bring you back to where you started. In such a universe, there would be no edge to escape from, no boundary to cross, just an endless journey through space that eventually curves back on itself. All of these factors, gravity's curvature of space-time, the expansion of space, time dilation, dark energy, quantum uncertainties, and the topology of space itself, work together to create a cosmos that appears to be fundamentally inescapable. It's as if the universe is a masterpiece of cosmic engineering, designed to be stable, interesting, and beautifully complex, but absolutely closed to emigration. Yet even within this cosmic prison, theoretical physics opens tantalizing windows to possibilities that stretch our understanding of what escape might mean. While the conventional physics of our universe seems to forbid any true departure from reality, the frontiers of theoretical science suggest pathways that might, under extraordinary circumstances, allow something like cosmic transcendence. These scenarios push us into realms where the familiar rules of space, time, and causality begin to break down in fascinating ways. Consider first the possibility of wormholes, theoretical tunnels through space-time that could connect distant regions of our universe or even link our universe to others entirely. Einstein and his colleague Nathan Rosen showed that the mathematics of general relativity permits these Einstein-Rosen bridges, though they would likely be incredibly unstable and would collapse before anything could travel through them. But some theoretical physicists have proposed that sufficiently advanced civilizations might be able to stabilize wormholes using exotic matter with negative energy density. If such constructions were possible, a wormhole might provide a shortcut not just across space, but potentially outside our universe entirely. Imagine stepping through a doorway and emerging not in another part of our cosmos, but in a completely different reality, with its own laws of physics, its own space-time, its own history. You wouldn't have escaped by outrunning the expansion of space. You would have taken a shortcut through the fabric of reality itself. Quantum mechanics offers another potential escape route through the phenomenon of quantum tunneling. In the quantum world, particles can sometimes appear on the other side of energy barriers that they don't have enough energy to climb over classically. They literally tunnel through the barrier, appearing on the other side without ever existing in the space between. Some speculative theories suggest that under extreme conditions, this tunneling effect might work on macroscopic or even cosmic scales. Could an entire universe quantum tunnel into a different state of existence? Could consciousness itself tunnel beyond the boundaries of space-time? These questions push quantum mechanics to its absolute limits, but they suggest possibilities that transcend our usual understanding of cosmic imprisonment. If reality itself is fundamentally quantum, then perhaps the boundaries we perceive as absolute are actually just very high energy barriers that might, under extraordinary circumstances, be tunneled through. The many worlds interpretation of quantum mechanics presents perhaps the most mind-bending escape scenario of all. If every quantum event spawns parallel universes, then you are constantly branching into countless versions across an infinite multiverse. In this view, escape from our universe isn't something you need to achieve. It's something that's happening continuously at the quantum level. Every moment, countless versions of you are splitting off into universes with slightly different histories, different physical laws, or different cosmic structures. String theory and theories of extra dimensions offer yet another class of escape scenarios. If our three-dimensional space is actually embedded in a higher dimensional space, what physicists call the bulk, then escape might involve finding a way to move through these extra dimensions. Just as a two-dimensional being trapped on the surface of a sphere might escape by moving in the third dimension, we might escape our three-dimensional cosmic prison by accessing the higher dimensions that string theory suggests exist all around us. Some versions of string theory propose that our entire universe is like a membrane, or brain, floating in a higher dimensional space, populated by other brains, other universes with which we normally cannot interact. Under certain conditions, these brains might collide or intersect, potentially allowing matter, energy, or information to pass between universes. Such brain collisions might even be responsible for cosmic events like the Big Bang itself. Even more speculatively, some theories suggest that consciousness itself might have properties that transcend the physical boundaries of space-time. If consciousness is somehow fundamental to the structure of reality, as some interpretations of quantum mechanics suggest, then it might be possible for conscious beings to access levels of existence that lie beyond the physical universe. This ventures into territory that borders on philosophy and mysticism, but it remains within the realm of serious theoretical consideration. Perhaps the most radical escape scenario involves the possibility that our entire universe is a simulation running on some vast cosmic computer. If we are indeed living in a simulated reality, then escape might not require traveling through space-time at all, but rather achieving some form of computational transcendence, breaking free from the program that defines our reality. While this scenario sounds like science fiction, it has been seriously considered by philosophers and even some physicists as a genuine possibility. Finally, there's the scenario that our understanding of physics itself is so fundamentally limited that true escape routes exist, but remain completely invisible to our current theories. Just as quantum mechanics revealed aspects of reality that were inconceivable to classical physics, perhaps there are aspects of existence that our current paradigms cannot even begin to imagine. The escape routes from the universe might be hiding in plain sight, waiting for the next revolution in human understanding to reveal them. These theoretical scenarios remind us that the boundaries of possibility are often defined more by the limits of our imagination and understanding than by the fundamental structure of reality itself. While cosmic escape remains beyond our current capabilities, the universe continues to surprise us with its depth, complexity, and potential for transcendence. Let's venture now into one of the most mind-expanding concepts in modern physics. The idea that our universe, vast and seemingly infinite as it appears to us, might be just one bubble in an endless cosmic foam of parallel realities. The multiverse hypothesis suggests that everything is far stranger and more magnificent than we ever dared imagine, with our entire cosmos representing merely a single note in an infinite symphony of existence. The simplest type of multiverse arises from a profound realization about infinity. If space extends infinitely in all directions, and many cosmological models suggest it does, then the number of possible arrangements of matter and energy, while astronomically large, is still finite. In an infinite space with finite possibilities, every possible configuration must not only occur somewhere, but must occur infinitely many times. This means there are infinite copies of you, of Earth, of our entire observable universe, scattered throughout the infinite expanse of space. Picture this. Somewhere out there, unimaginably far away, there's another version of you listening to these exact words. But in that parallel region, perhaps you decided to have tea instead of coffee this morning. Or perhaps dinosaurs never went extinct on that version of Earth. In an infinite universe, there are versions of you making every possible choice, living every possible life, experiencing every possible variation of existence. Some of these parallel U's differ by only the smallest quantum events, while others exist in regions where the entire history of matter and energy unfolded differently. But this is just the beginning. Quantum mechanics introduces us to what physicist Hugh Everett called the many-worlds multiverse. Every time a quantum event occurs, every time an electron chooses which path to take, every time a particle decays, every time any quantum possibility becomes actuality, the universe splits into parallel branches, each containing a different outcome. This suggests that reality is like a vast tree, constantly branching with every quantum event, creating an infinite number of parallel worlds where every possible quantum outcome actually occurs. In the many-worlds multiverse, there are versions of reality where you decided not to listen to this story tonight, where humans never evolved, where the laws of physics are subtly different because different quantum outcomes shaped the early universe. Some branches of this quantum multiverse might be nearly identical to ours, while others might be so foreign that we couldn't recognize them as reality at all. Then there's what cosmologists call the eternal inflation multiverse, which emerges from our understanding of the Big Bang itself. If the inflationary period that marked the beginning of our universe is still continuing in other regions of space-time, then new universes are constantly being born in an endless process of cosmic reproduction. Each of these bubble universes might have different physical constants, different numbers of dimensions, different fundamental forces. Imagine soap bubbles forming on the surface of an infinite ocean, each bubble representing a complete universe with its own space, time, and physical laws. Our universe would be just one such bubble, floating alongside countless others in what physicist André Linde calls the multiverse of eternal inflation. Some bubbles might be similar to ours, capable of forming stars and planets, and perhaps even life. Others might be so different that matter as we know it couldn't exist there at all. String theory adds yet another layer to the multiverse concept through what physicists call the landscape of possible universes. String theory suggests that there might be as many as 10 circumflex, 500 different ways that the extra dimensions required by the theory could be compactified or curled up. Each different configuration would create a universe with different physical laws, different particles, different forces. The number 10 circumflex 500 is so large that it exceeds the number of atoms in our observable universe by a factor that defies comprehension. In the string theory multiverse, every possible set of physical laws that string theory allows actually exists somewhere. There are universes where gravity is stronger or weaker, where electrons have different masses, where time flows at different rates, where the very concept of matter and energy takes forms we cannot imagine. Our universe, with its particular combination of physical constants that allow for stars, planets, and life, would be just one point in this vast landscape of possibilities. There are universes where gravity is stronger or weaker. Some theories even suggest a mathematical multiverse, where every mathematically consistent set of laws exists as a physical reality. In this most expansive vision of the multiverse, not only does every possible physics exist, but every possible mathematics becomes real. There would be universes based on geometries we've never discovered, operating according to logical systems we've never imagined. And what makes these multiverse theories particularly intriguing is that they arise naturally from some of our most successful scientific theories. We don't need to invent new physics to get a multiverse. We get multiverses as inevitable consequences of taking our current theories seriously. Quantum mechanics seems to demand many worlds. Inflation theory seems to produce eternal bubble creation. String theory seems to require a vast landscape of possibilities. Yet these parallel realities remain tantalizingly beyond our direct reach. If they exist, they are separated from us by barriers that might be fundamentally uncrossable, infinite distances, different spacetimes, or the quantum branching that makes parallel worlds causally disconnected from our own. We might be surrounded by infinite realities, infinite possibilities, infinite versions of existence, yet remain forever unable to visit them or even confirm their existence. Imagine the most magnificent soap bubble you've ever seen. iridescent and perfect, floating gently through the air. Now imagine that this bubble contains within it all of space and time, every star and galaxy, every planet and possibility, everything that has ever existed or ever could exist. This bubble is our universe. And now imagine that it's floating not through air, but through an infinite cosmic foam, where countless other bubbles are constantly forming, each one a complete universe with its own unique properties and possibilities. This is the breathtaking vision of cosmic reproduction, suggested by eternal inflation theory. According to this model, the rapid expansion that marked the beginning of our universe, the inflationary period, never actually ended everywhere. While inflation stopped in our region of space-time 13.8 billion years ago, allowing our universe to slow down and begin the process of forming matter and structure, inflation continues in other regions, constantly spawning new universes in an endless process of cosmic birth. The mechanism behind this cosmic reproduction is as elegant as it is mind-bending. The field that drives inflation, let's call it the inflaton field, exists in different energy states in different regions of space. In most regions, this field sits in a high energy state that causes space to expand exponentially. But occasionally, through quantum fluctuations, the field drops to a lower energy state in small pockets of space. When this happens, inflation stops in that region, and a new universe begins its more sedate expansion, eventually cooling enough to form atoms, stars, and galaxies. Each of these bubble universes is like a calm lagoon in an ocean of cosmic storms, while the space between bubbles continues to inflate exponentially, carrying them apart faster than light can travel between them. The space inside each bubble follows the more familiar expansion we observe in our own universe. From inside any bubble, the universe appears finite in age but potentially infinite in extent, with a cosmic microwave background, galaxy formation, and all the features we recognize as cosmic evolution. What makes this picture particularly fascinating is the diversity it predicts among bubble universes. The process that ends inflation in any given region is random, governed by quantum fluctuations that can produce different outcomes. Some bubbles might have physical constants similar to ours, the same strength of gravity, the same mass for electrons, the same speed of light, but others might have completely different values for these fundamental parameters. Consider a bubble universe where gravity is 10 times stronger than in ours. Stars in such a universe would burn through their fuel much more quickly, and planets would need to orbit much closer to their suns to maintain liquid water. Life, if it could exist at all, would evolve under completely different constraints. Or imagine a bubble where the electromagnetic force is weaker, atoms might be larger, chemistry might work differently, and the very concept of solid matter might be alien to their version of physics. Some bubble universes might be even more exotic. There could be bubbles with different numbers of spatial dimensions, where geometry works in ways we can barely imagine. There might be bubbles where time flows backward, or where the distinction between space and time is fundamentally different from our experience. The space of possibilities is vast, and if eternal inflation is correct, all of these possibilities are realized somewhere in the multiverse. The distances between these bubble universes boggle the mind. Even if two bubbles formed at nearly the same time in cosmic history, the exponential expansion of the space between them would carry them apart so quickly that light from one could never reach the other. They become causally disconnected, separate realities that can never influence each other, never communicate, never even know of each other's existence. Each bubble universe is an island of causality in an ocean of exponentially expanding space. This cosmic reproduction process has no beginning and no end. It has been going on for infinite time and will continue for infinite time, constantly creating new bubbles, new universes, new possibilities. Our universe is neither the first nor the last, neither special nor typical. It's simply one random sample from an infinite collection of cosmic experiments, each testing different combinations of physical laws and initial conditions. The implications of this endless cosmic reproduction are both humbling and exhilarating. Every possible universe that can exist does exist, somewhere in the multiverse. Every variation of physical laws, every different outcome of cosmic evolution, every alternative history is being played out in some bubble universe. If you've ever wondered what if the universe were different in some fundamental way, eternal inflation suggests that there's a bubble universe where it is different in exactly that way. Yet these parallel realities remain forever beyond our reach. The exponential expansion that creates them also ensures their eternal separation. We can theorize about them, calculate their properties, and imagine their exotic physics, but we can never visit them, observe them directly, or receive any signals from them. They exist in the same way that dinosaurs exist, as real parts of the universe's history, but accessible to us only through indirect evidence and theoretical understanding. In this view, our universe is like a single cell in an infinite organism, contributing to a cosmic biology we can barely begin to comprehend. We are part of a reproductive process that spans infinite space and infinite time, creating endless variations on the theme of existence itself. Now let's descend into the quantum realm, where the very foundations of reality become probability clouds, and the act of observation literally creates the world we experience. Here, in the deepest level of physical reality, we encounter the most radical version of the multiverse, one where every possible outcome of every quantum event creates a new branch of reality, leading to an ever-expanding tree of parallel worlds that contains every possible version of existence. At the heart of quantum mechanics lies a profound mystery. Before we observe a quantum system, it exists in what physicists call a superposition of all possible states simultaneously. An electron can be spinning both clockwise and counterclockwise at the same time. A photon can take all possible paths through space simultaneously. A radioactive atom can be both decayed and not decayed until the moment we check on it. This isn't just a limitation of our knowledge. It appears to be a fundamental feature of reality itself. But what happens when we make an observation and collapse this superposition into a single definite state? The traditional interpretation of quantum mechanics says that all the other possibilities simply vanish, like roads not taken. But physicist Hugh Everett proposed something far more radical in the 1950s. What if none of the possibilities ever disappear? What if every possible outcome of every quantum event actually occurs, but in parallel realities that we can no longer access? In Everett's many worlds interpretation, the universe is constantly branching at the quantum level every time a quantum measurement occurs, and quantum measurements are happening trillions of times per second throughout the universe. Reality splits into parallel branches, each containing a different outcome. The version of you reading this right now is just one branch in an impossibly vast tree of parallel selves, each experiencing a slightly different version of reality. This quantum multiverse is almost impossible to visualize because of its sheer scope. Consider just the quantum events happening in your brain right now as you process these words. Every neuron firing, every chemical reaction, every molecular interaction involves countless quantum processes. Each of these processes has multiple possible outcomes, and if the many worlds interpretation is correct, each outcome occurs in some parallel branch of reality. This means there are versions of you where your neurons fired slightly differently a moment ago, leading to subtly different thoughts or decisions. There are branches where you decided to stop reading this paragraph earlier, branches where you fell asleep, branches where you never discovered this video in the first place. The quantum branching creates a vast space of parallel possibilities, most differing from our branch by only the smallest quantum events, but some diverging dramatically over time. The mathematics of quantum mechanics suggests that these parallel branches are all equally real. There's no preferred branch, no true version of reality, just countless parallel stories being written simultaneously across the quantum multiverse. What we experience as reality is simply our particular path through this endless garden of forking possibilities. But the quantum multiverse goes deeper than just parallel versions of familiar reality. Quantum mechanics also governs the behavior of fields and particles throughout the universe, including during the crucial moments after the Big Bang, when the fundamental properties of our cosmos were being determined. If many worlds is correct, then there are parallel universes where the quantum events of the early cosmos unfolded differently, leading to universes with different physical constants, different numbers of dimensions, different fundamental forces. Some of these quantum-generated parallel universes might be so similar to ours that the differences are undetectable. Others might be alien beyond imagination, realities where the basic structure of matter and energy took completely different forms based on different quantum outcomes in the primordial universe. There might be branches where stars never formed, where gravity works differently, where the very concept of space and time emerged in unfamiliar ways. The quantum multiverse also raises profound questions about identity and continuity. If there are countless versions of you making slightly different decisions in parallel realities, which one is the real you? The answer, according to many worlds, is that they all are. You are not a single individual, but rather a vast collection of parallel selves spread across the quantum multiverse, each experiencing their own version of existence. This leads to what some philosophers call quantum immortality, the idea that consciousness might always experience the branches where it survives. In any situation where you might die, there would presumably be some quantum branches where unlikely events conspire to save you. If consciousness only experiences the branches where it continues to exist, then from your subjective perspective, you might be functionally immortal, always finding yourself in the branches where you survive, against increasingly improbable odds. The quantum multiverse challenges our most basic intuitions about reality, identity, and existence. It suggests that the universe is far stranger and more magnificent than we can easily comprehend, a place where every possible story is being told simultaneously, where every decision creates new worlds, where the very act of existing generates infinite variations on the theme of consciousness. Yet these parallel quantum worlds remain completely inaccessible to us. Once the branches separate, they can never reconnect or communicate. We are forever trapped in our particular branch of the quantum tree, able to theorize about our parallel selves, but never able to meet them or confirm their existence directly. Let's embark on a journey that will challenge your most fundamental assumptions about the nature of space itself. We often think of space as simply empty, a vast, three-dimensional container in which matter and energy play out their cosmic drama. But space itself has a shape, a geometry that determines not just how objects move through it, but whether concepts like outside the universe or escaping reality even make sense. The shape of space is perhaps the most profound geometric question we can ask about existence itself. Imagine you're a two-dimensional being living on a surface, unable to perceive the third dimension that might curve your world. If you lived on a flat, infinite plane, you could travel in any direction forever without ever reaching an edge or returning to your starting point. But if you lived on the surface of a sphere, you could also travel forever in any direction, yet eventually you would find yourself back where you started, having circumnavigated your curved world without ever encountering a boundary. Now extend this analogy to our three-dimensional space. Just as a two-dimensional surface can be flat or curved in 3 dimensions, our three-dimensional space might be curved in a fourth spatial dimension that we cannot directly perceive. The geometry of this curvature determines the ultimate fate of the universe and whether escape from it is even a meaningful concept. Einstein's general relativity tells us that the geometry of space is determined by the amount and distribution of matter and energy it contains. If the universe contains exactly the critical density of matter and energy, space will be flat, extending infinitely in all directions with the familiar Euclidean geometry we learned in school. In such a universe, parallel lines never meet. The angles of triangles always add up to 180 degrees, and space continues forever without boundary or edge. But if the universe contains more than this critical density, something magnificent and strange occurs. Space curves back on itself, creating what mathematicians call closed, positively curved geometry. Picture the surface of a sphere, scaled up to 3 dimensions. In such a universe, if you could travel far enough in any direction, you would eventually return to your starting point, having circumnavigated the entire cosmos. Parallel lines would eventually converge, and triangles would have angles that sum to more than 180 degrees. The third possibility is equally fascinating. If the universe contains less than the critical density of space, would have negative curvature, like a three-dimensional version of a saddle shape. In such a universe, space would be infinite, but its geometry would be hyperbolic rather than flat. Parallel lines would diverge from each other. Triangles would have angles summing to less than 180 degrees, and the volume of space would grow faster than in a flat universe. Current observations suggest that our universe is remarkably close to being perfectly flat, so close that we cannot yet determine with certainty which of these three geometries describes reality. This near flatness is itself a profound puzzle, because most initial conditions would have led to universes that are obviously curved one way or the other. The fact that we live in a universe balanced right at the boundary between positive and negative curvature may be a clue about the cosmic inflation that occurred in the universe's first moments. The geometry of space has profound implications for the question of cosmic escape. In a flat or negatively curved universe, space extends infinitely in all directions. There are no boundaries to cross, no edges to escape from, just endless space stretching forever. But the concept of escape becomes ambiguous when there's nowhere to escape to. If space itself is infinite, then outside the universe is not a location, but a meaningless concept. In a positively curved, closed universe, the situation is even more intriguing. Such a universe would have finite volume, but no boundaries, like the surface of a sphere, but in 3 dimensions instead of 2. You could travel in any direction forever, but you would never reach an edge because there are no edges to reach. Instead, you would eventually return to your starting point, having completed a grand circuit of the entire universe. This raises a beautiful question. In a closed universe, what would it mean to escape? You could travel as far as you wanted in any direction, but you would always remain within the same finite volume of space. It would be like trying to escape from the surface of the Earth by walking. No matter how far you walk, you remain on the same planetary surface. The only way to truly escape would be to find a path through a dimension perpendicular to the 3-dimensional space of the universe itself. The geometry of space also affects how we understand the expansion of the universe. In a flat universe, expansion means that the distances between objects increase forever. In a closed universe, expansion might eventually reverse into contraction, leading to a big crunch where all of space collapses back into a point. In an open, negatively curved universe, expansion would continue forever, with space growing increasingly sparse and cold. But perhaps most mysteriously, we must consider the possibility that the true geometry of space operates on scales much larger than our observable universe. The cosmic microwave background gives us information about the curvature of space only within our cosmic horizon. The universe as a whole might have a completely different geometry, with curvature that becomes apparent only on scales vastly larger than anything we can observe. The shape of space fundamentally transforms what we mean when we ask about escaping the universe, because geometry itself determines whether concepts like outside, beyond, or exterior to everything can have any meaning at all. It's a puzzle that sits at the intersection of mathematics, physics, and philosophy, challenging us to think about existence in ways that stretch language itself to its breaking point. Consider first the most intuitive case: a flat, infinite universe. In such a cosmos, space extends forever in all directions, containing an infinite amount of matter and energy distributed throughout an infinite volume. Or, here, the question, what lies outside the universe, becomes as meaningless as asking what number comes after infinity. There is no outside, because outside implies a boundary, and infinite space has no boundaries to speak of. Every point in this infinite expanse is a valid location within the universe, and there are no additional points that could constitute an exterior realm. In such a universe, the very concept of escape becomes paradoxical. You could travel forever in any direction, covering infinite distances and exploring infinite reaches of space, but you would never approach any kind of boundary or edge. Escape requires something to escape from, some kind of containment to break free of. But infinite space provides no such containment. It's like trying to escape from the concept of number itself. Where would you go that wouldn't still be within the mathematical realm you're trying to leave? But the situation becomes even more philosophically rich when we consider a closed, finite universe with positive curvature. Imagine space curved back on itself in all three dimensions, creating a cosmic analog to the surface of a sphere. Such a universe would have finite volume but no boundaries. Every point within it would be a perfectly valid location, with no edges, walls, or barriers anywhere to be found. In this closed universe, outside becomes a concept that might exist mathematically, but cannot be reached by traveling through space. Just as the surface of a sphere has no boundaries yet can be embedded in three-dimensional space, our three-dimensional universe might have no boundaries yet still be embedded in some higher dimensional space. The outside would lie in dimensions perpendicular to our three-dimensional reality, dimensions we cannot access by moving through the space we know. This creates a fascinating possibility. In a closed universe, you could potentially escape, not by traveling to infinity, but by finding a way to move through these additional dimensions. It would be like a two-dimensional being learning to jump off the surface of their spherical world into the third dimension. The escape wouldn't involve crossing a boundary within space, but rather discovering directions of movement that transcend space itself. The topology of space adds another layer of complexity to these considerations. Topology is the branch of mathematics that studies the properties of shapes that persist even when the shapes are stretched or deformed. A sphere and a cube have different geometries, but the same topology. They're both closed surfaces without boundaries. But a sphere and a donut have different topologies because the donut has a hole through its center. Our universe might have exotic topological properties that make the concept of outside even stranger, and space might be finite, but multiply, connected, like a cosmic hall of mirrors, where traveling far enough in one direction brings you back to the same location from a different angle. Or space might have a topology, like a Klein bottle or a projective plane, mathematical objects that twist back on themselves in ways that challenge our three-dimensional intuitions. In some topological scenarios, the universe might be like a vast cosmic donut, where traveling far enough in any direction eventually brings you back to your starting point. But along the way, you might encounter multiple copies of the same regions of space, seen from different perspectives. In such a universe, escape might involve not leaving space entirely, but finding the topological pathways that connect distant regions of the cosmos. The whole, the shape of space, also determines how information and causality propagate through the universe. In a flat universe, cause and effect can spread infinitely far, though limited by the speed of light. In a closed universe, causal influences can potentially circumnavigate the entire cosmos, allowing events to eventually influence their own past in strange temporal loops. In multiply connected spaces, information might take unexpected routes, creating cosmic shortcuts that could provide pathways for something resembling escape. Perhaps most intriguingly, the shape of space might not be fixed or uniform. Some theories suggest that space itself might be dynamic, changing its geometry over time or having different curvatures in different regions. The space near massive objects is already curved by gravity. Perhaps there are regions of the universe where space is so severely curved that it creates bridges or tunnels to other spaces entirely. The relationship between the shape of space and the possibility of escape ultimately points to a deeper truth. Our concepts of inside and outside, contained and free, are human constructs that may not apply to the universe as a whole. The cosmos might be so fundamentally different from our everyday experience that the very question of escape needs to be reconsidered from the ground up, taking into account geometries and topologies that stretch our imagination to its limits. Now let's venture into one of the most mind-bending possibilities in cosmology: the idea that our seemingly infinite universe might actually wrap around itself in ways so subtle and grand that we haven't yet detected the cosmic pattern. Imagine discovering that space itself is like a vast, three-dimensional version of a video game, where traveling far enough in one direction brings you back to where you started, but from an unexpected angle. This is the realm of cosmic topology, where the universe might be far stranger and more interconnected than we ever imagined. To understand cosmic topology, let's start with a simple analogy. Imagine you're a character in an old-style video game, walking across what appears to be an infinite landscape. But suddenly, when you walk off the right edge of the screen, you reappear on the left side, walk off the top, and you emerge from the bottom. The surface topology was that of a torus, a donut shape, even though it appeared flat and endless from within. Our universe might work similarly. Space might be finite in volume, but without boundaries, connected to itself through topological relationships that make distant regions of the cosmos neighbors in ways we don't expect. If you could travel far enough in one direction, trillions upon trillions of light years, you might eventually see the back of your own head, having circumnavigated the entire universe. The most straightforward example of this is a universe with the topology of a three-dimensional torus, just as the surface of a donut can be unrolled into a flat rectangle where opposite edges are identified with each other. Space itself might be like a cosmic rectangular box where traveling out one face brings you in through the opposite face. In such a universe, there would be multiple copies of every object scattered throughout space, not physical copies, but the same objects seen from different topological perspectives. Imagine looking up at the night sky in such a universe. You might see the same galaxy in multiple directions, each image showing that galaxy at a different time in its history, because the light took different paths through the wrapped space to reach you. You might even see multiple images of the Milky Way itself, each one showing our galaxy as it appeared at different epochs, creating a kind of cosmic hall of mirrors where the universe observes itself from all possible angles. But cosmic topology can be far more exotic than simple torus wrapping. Space might have the topology of a Klein bottle, a surface that connects to itself in a way that eliminates the distinction between inside and outside. In a Klein bottle universe, the concepts of interior and exterior would lose their meaning entirely. Every point would be simultaneously inside and outside, making the question of cosmic escape not just difficult but literally nonsensical. Or consider the possibility of a universe with the topology of a Poincare dodecahedral space, a shape constructed by identifying the faces of a regular dodecahedron in a specific pattern. Such a universe would be finite, but unbounded, and incredibly rich in its topological structure. Traveling in certain directions would bring you back to your starting point after covering vast distances, but the return journey would reveal space twisted and rotated in unexpected ways. The search for cosmic topology presents one of the most intriguing detective stories in modern cosmology. If our universe has non-trivial topology, we should be able to detect it by looking for patterns in the cosmic microwave background radiation. Regions of the early universe that were actually the same region, connected through the topology of space, should show identical temperature patterns in the CMB. Finding such matching patterns would be like discovering cosmic fingerprints that reveal the true shape of reality. Some cosmologists have claimed to find hints of dodecahedral topology in the CMB data, though these claims remain controversial. The challenge is that cosmic topology effects would be most apparent on the largest observable scales, where our measurements are least precise and most affected by uncertainties. We're essentially trying to determine the shape of a vast cosmic container by examining subtle patterns in its contents. If our universe does have non-trivial topology, it would profoundly affect the meaning of cosmic escape. In a multiply-connected universe, escape might not require leaving space entirely, but rather finding the topological pathways that connect distant regions. You might escape our local region of the universe by discovering how to navigate the cosmic wraparound, emerging in what appears to be a completely different part of the cosmos, but is actually the same space viewed from a different topological perspective. This raises fascinating questions about the nature of exploration and discovery in a topologically complex universe. If space wraps around itself, then any journey to the edge of our observable universe might actually be a journey toward an earlier version of our own cosmic neighborhood. The most distant galaxies we observe might be younger versions of galaxies much closer to home, seen through the funhouse mirror of cosmic topology. The possibility of cosmic topology also suggests that the universe might be far more interconnected than we realize. What appear to be isolated regions of space, separated by vast distances, might actually be intimately connected through the hidden geometry of space itself. In such a universe, the concept of cosmic loneliness, the idea that we are forever isolated from distant regions by the expansion of space, might be an illusion created by our failure to recognize the universe's true topological structure. As we approach the deepest mysteries of cosmic escape, we enter a realm where the very language of physics begins to strain under the weight of concepts that push against the boundaries of what can be known, calculated, or even meaningfully discussed. Here, at the event horizon of existence itself, our most sophisticated theories offer glimpses of possibilities so strange that they challenge not just our understanding of the universe, but our understanding of understanding itself. Let's begin with what we know about event horizons from black holes, those cosmic laboratories where space-time becomes so severely curved that it creates genuine boundaries between the knowable and the unknowable. At the event horizon of a black hole, something remarkable happens to the concepts of space, time, and causality. From the perspective of someone falling past the event horizon, nothing seems particularly special about crossing this boundary. Space and time continue to behave normally, at least initially. But from the perspective of someone watching from outside, the falling observer appears to slow down, redshift, and fade away, frozen forever at the moment of crossing. This dual perspective hints at something profound about the nature of boundaries in general relativity. The event horizon represents a point of no return, not because space-time becomes singular there, but because the very structure of causality changes. Information that crosses the event horizon can never return to the outside universe. It's not just practically impossible to escape, it's theoretically meaningless to speak of escape because the causal structure of space-time forbids it. Now imagine scaling this concept up to the universe as a whole. If our cosmos has boundaries, whether spatial, temporal, or causal, then crossing them might involve similar transformations of the fundamental structure of reality. Just as falling past a black hole's event horizon doesn't necessarily feel dramatic to the person experiencing it, crossing the boundary of the universe might not involve any sudden change in local physics. The drama lies not in the crossing itself, but in the fundamental alteration of what becomes possible afterward. General relativity suggests that space-time itself can have boundaries, edges where the mathematical description of reality simply stops making sense. These aren't boundaries in space, but boundaries of space, places where the very concept of location breaks down. Crossing such a boundary wouldn't mean traveling to a different place, but potentially traveling to a realm where the concept of place itself no longer applies. Quantum mechanics adds another layer of strangeness to boundary crossing scenarios. The quantum vacuum, what we think of as empty space, is actually a seething foam of virtual particles popping in and out of existence. At the boundary of the universe, if such a boundary exists, the quantum vacuum might behave differently. Virtual particles that normally annihilate each other might be separated by the boundary, potentially creating real particles from the quantum foam. Crossing a cosmic boundary might literally create matter and energy from nothingness. String theory, our most ambitious attempt to unify all of physics, suggests possibilities that are even more exotic. In string theory, the fundamental constituents of reality are not point particles, but tiny vibrating strings. These strings exist in multiple dimensions, beyond the three spatial dimensions we experience. Crossing the boundary of our universe might involve accessing these extra dimensions, allowing for types of motion that are literally impossible within our familiar three-dimensional space. Some interpretations of string theory suggest that our entire universe might be a three-dimensional surface, a brain, floating in a higher dimensional space. If this is true, then crossing the boundary of our universe might mean leaving our brain and entering the bulk space that contains it. The physics of the bulk might be completely different from the physics on our brain, with different forces, different particles, and different rules governing how matter and energy behave. But perhaps the most mind-bending possibility emerges from attempts to quantize gravity itself. to create a quantum theory that describes the behavior of space-time at the smallest scales. In quantum gravity, space and time themselves might be emergent properties of something more fundamental. At the Planck scale, distance is so small that quantum effects dominate gravitational physics. Space-time might dissolve into a quantum foam where the concepts of distance and duration lose their meaning. Crossing the boundary of the universe in a quantum gravity scenario might involve transitioning from the emergent space-time we experience to the more fundamental quantum substrate from which space-time arises. It would be like discovering that what you thought was solid matter is actually a pattern of waves on an ocean, and then finding a way to dive beneath the surface of that ocean into the deeper reality that creates the waves. (4) The physics of boundary crossing also involves profound questions about information and entropy. The holographic principle, inspired by black hole physics, suggests that all the information in a three-dimensional region of space can be encoded on its two-dimensional boundary. If our universe has boundaries, they might contain all the information about everything within our cosmic region encoded in their structure. Crossing such a boundary might involve a fundamental transformation of how information itself is organized and processed. Yet all these theoretical possibilities come with a crucial caveat. We don't even know if cosmic boundaries exist, let alone what crossing them might entail. The physics of boundary crossing remains largely speculative, pushing our theories into regimes where they haven't been tested and may not even be applicable. At the edge of everything, where the familiar laws of physics begin to whisper rather than shout their certainties, we encounter something both terrifying and magnificent: the complete breakdown of our most cherished theories about how reality works. Here, in the conceptual space where cosmic escape might be possible, the mathematics that normally guides us becomes as unreliable as a compass near the magnetic pole, spinning wildly as it encounters something beyond its ability to measure or comprehend. The first casualty in this breakdown is often our concept of space-time itself. Einstein's general relativity, which has served us so well in describing everything from GPS satellites to black holes, begins to produce infinite values and undefined results when pushed to its ultimate limits. At the singularities inside black holes, or at the moment of the Big Bang, the equations literally break down, giving us nonsensical answers like infinite density and infinite curvature. These aren't just computational difficulties, they're signs that our theory is encountering something for which it simply wasn't designed. Imagine trying to use a map to navigate in a place where the very concept of geography breaks down. The map works perfectly well for familiar territories, but when you reach the edge of the mapped world, you find only the ancient cartographer's warning, "Here be dragons." At the boundaries of physics, we encounter our own versions of dragons, phenomena that our theories cannot describe, predict, or even properly formulate as questions. Quantum mechanics, our other pillar of modern physics, faces its own dragons at cosmic boundaries. The quantum field theory that describes particles and forces works beautifully within the familiar space-time of our universe. But what happens to these fields at the edge of space itself? Can quantum fields exist where space-time becomes undefined? Do particles have meaning in a realm where the concepts of position and momentum lose their significance? The marriage of quantum mechanics and general relativity, quantum gravity, represents our most ambitious attempt to venture into dragon territory, but it remains frustratingly incomplete. String theory, loop quantum gravity, causal set theory, and other approaches each offer glimpses of what might lie beyond our current understanding, but none provide a complete picture. They're like flashlights illuminating small patches of an enormous cave, each revealing fascinating details, but leaving most of the cavern in darkness. At the deepest level, the breakdown of physics at cosmic boundaries reveals something profound about the nature of physical law itself. Our theories aren't just descriptions of reality, they're descriptions of particular types of reality. Reality with certain assumed properties like continuity, locality, and causality. When we approach regions where these assumptions might not hold, our theories naturally begin to fail. Consider the assumption of locality, the idea that objects can only be directly influenced by their immediate surroundings. This assumption underlies almost all of classical physics, but quantum mechanics already shows us situations where locality appears to be violated through quantum entanglement. At cosmic boundaries, the very notion of local and distant might become meaningless, requiring us to develop entirely new ways of thinking about how events influence each other. The concept of causality, the idea that causes precede effects in a well-defined temporal order, faces similar challenges. In extreme gravitational fields, time dilation can stretch moments into eternities. At cosmic boundaries, the flow of time itself might become so distorted that cause and effect lose their usual relationship. We might need to develop physics that doesn't rely on a clear temporal ordering of events. Even more fundamentally, our mathematics itself might prove inadequate for describing reality at its deepest levels. Mathematics is based on concepts like number, continuity, and logical consistency that might not apply to the substrate from which our universe emerges. Just as ancient mathematicians struggled to understand irrational numbers and had to expand their concept of what numbers could be, we might need to expand our concept of what mathematics itself can be. The breakdown of physics at cosmic boundaries also raises questions about the nature of physical constants, those fundamental numbers like the speed of light, Planck's constant, and the gravitational constant that appear in our equations. Are these truly constant throughout all of reality, or are they local properties of our particular cosmic region? If physics breaks down at cosmic boundaries, perhaps the constants that define our version of physics give way to different constants, or to a realm where the very concept of fixed physical law doesn't apply. This breakdown isn't necessarily a failure of human knowledge. It might be an inevitable consequence of the universe's structure, just as Gödel's incompleteness theorems show that mathematics itself contains truths that cannot be proven within mathematical systems. The universe might contain aspects of reality that cannot be understood through physical theories operating within that reality. The breakdown of known physics at cosmic boundaries suggests that escaping the universe, if possible at all, would involve more than just traveling to a different location or even a different space-time. It might require a fundamental transformation of the very categories through which we understand existence: space, time, matter, energy, causality, and even logic itself. In this view, the ultimate cosmic escape wouldn't be a journey through space or time, but a journey beyond the concepts that make space and time meaningful, into a realm where reality operates according to principles so alien to our experience that we lack even the vocabulary to describe them. As we stand at the precipice of cosmic escape, peering into realms that exist beyond the boundaries of our universe, we must confront a possibility that is both humbling and exhilarating. The journey beyond our cosmic horizon might require not just new physics, but entirely new ways of understanding what understanding itself means. The tools of comprehension that have served us so well within our universe, logic, mathematics, the scientific method, even consciousness itself, might need to be transformed in ways we can barely imagine. Consider how our current understanding is fundamentally shaped by existing within a universe with 3 spatial dimensions and 1 temporal dimension. Our entire mathematical framework, from basic geometry to advanced quantum field theory, is built upon this dimensional foundation. Our logic is structured around concepts of identity and difference that make sense in a reality where objects have defined locations and distinct boundaries. Our language itself evolved to describe relationships between entities existing in space and time. But what if escaping the universe means entering a realm where these basic categories no longer apply? Imagine trying to understand a reality with 17 spatial dimensions, or where time flows in spirals rather than lines, or where the distinction between observer and observed completely dissolves. Our familiar tools of comprehension might be as inadequate as trying to measure the ocean with a ruler or capture a symphony with a camera. The transformation of understanding might begin with mathematics itself. The mathematics we use to describe our universe, calculus, geometry, algebra, assumes continuity, dimensionality, and logical consistency. But mathematics might be far more plastic than we realize. Just as non-Euclidean geometries revealed new ways of thinking about space, escaping our universe might require developing entirely new forms of mathematics based on principles we haven't yet discovered. Perhaps we would need mathematics that doesn't assume a clear distinction between discrete and continuous, or mathematical systems that allow for contradictions without collapsing into nonsense. We might need to develop numerical systems that go beyond infinity, or geometric frameworks that describe shapes existing in non-dimensional spaces. The mathematics of cosmic escape might be as different from our current mathematics as quantum mechanics is from the physics of thrown stones. Logic itself might need to be reconstructed, because our binary logic, where statements are either true or false, works well in a universe with clearly defined states and outcomes. But in a realm beyond space and time, the concept of definite states might become meaningless. Benign de seasons and trocent in univer, that prosent the folv, logic itself might need to be reconstructed. Our binary logicita, where statements are either true or false, works well in a universe with clearly defined states and outcomes. We might need to develop forms of reasoning that can handle fundamental uncertainty, where every statement exists in superposition between true and false, or where truth itself has additional dimensions beyond our familiar binary categorization. The scientific method, our most powerful tool for understanding reality, is built upon the assumption that reality is consistent, that experiments can be repeated, and that patterns discovered in one context will apply in similar contexts. But beyond the universe, these assumptions might not hold. Reality might be fundamentally unpredictable, unrepeatable, or so richly contextual that no universal patterns exist. We might need to develop entirely new methodologies for investigating realms where the scientific method itself becomes meaningless. Language, too, would need transformation. Our words and concepts are tools forged in the fires of three-dimensional existence, designed to describe relationships between separate objects moving through space and time. But cosmic escape might require us to describe realities where separation itself is meaningless, where change occurs without time, where existence and non-existence become indistinguishable categories. We might need to develop languages based on principles we can barely imagine, languages that convey meaning through relationships rather than objects, communication systems that operate outside the linear sequence of time, or forms of expression that transcend the boundary between the messenger and the message. The language of cosmic escape might be as different from human language as symphonies are from shopping lists. Perhaps most profoundly, consciousness itself might need to evolve. Our awareness is intimately connected to our embodied existence in space and time. Our sense of self is built around being a continuous entity persisting through temporal sequence, distinct from other entities and the environment around us. But if cosmic escape involves transcending space and time, then consciousness might need to transcend its current boundaries as well. We might need to develop forms of awareness that don't depend on the subject-object distinction, ways of knowing that don't require the separation of the knower from the known. The consciousness capable of cosmic escape might be as different from our current awareness as our awareness is from the information processing of a simple computer. Solve, but simple computer. This transformation of understanding might not be just a philosophical exercise. It might be a practical necessity. Just as space travel required humanity to develop new technologies, new mathematics, and new ways of thinking about motion and energy, cosmic escape might require evolution of consciousness itself. We might need to become something fundamentally different from what we are now, not just in terms of our technology or knowledge, but in terms of the very nature of our being. The question then becomes, would the consciousness capable of cosmic escape still be recognizably human, or would it be something so transformed that it represents a new form of existence entirely, one that we can no more comprehend from our current perspective than a bacterium can comprehend the experience of reading poetry under starlight? Perhaps this transformation is already beginning, in the quantum mechanics that challenges our classical intuitions, in the cosmology that reveals universes beyond imagination, in the mathematics that describes realities we cannot visualize, and in the growing recognition that reality is far stranger and more wonderful than our everyday experience suggests. There's a profound melancholy that settles over you when you truly grasp the scope of our cosmic isolation. We live in what astronomers call a Hubble bubble, a sphere of visibility beyond which the expansion of space carries matter away from us, faster than light can bridge the growing gaps. This isn't just a technological limitation that better telescopes might someday overcome. It's a fundamental feature of reality itself. We are cosmic islanders, forever separated from vast realms of existence by barriers written into the very structure of space and time. Picture yourself standing on a small island as the sea level rises around you. At first, you can still see other islands in the distance, perhaps even swim to them if you're determined enough. But as the waters rise, those distant shores fade beyond the horizon, one by one, until you're left alone on your shrinking patch of land, surrounded by an ocean that stretches beyond all possibility of crossing. This is our situation in the cosmos, except that instead of rising water, it's expanding space that isolates us from increasingly vast regions of existence. The cosmic microwave background radiation surrounds us like a spherical wall of ancient light, marking the boundary of the observable universe. Beyond this wall lie realms that are not just distant, but fundamentally unreachable. No signal we send could ever reach them, and no information from them could ever reach us. It's as if reality itself has drawn a circle around us and whispered, "This is your world. Everything beyond this boundary might as well not exist for you." What makes this isolation particularly poignant is that we know, or at least strongly suspect, that incredible things are happening beyond our cosmic horizon. Galaxies are forming, stars are being born and dying, planets are developing their own unique chemistries, and perhaps their own forms of life. There might be civilizations out there, solving mysteries we haven't even discovered yet, creating art that would take our breath away, or developing technologies that seem like magic from our perspective. All of this cosmic drama unfolds in regions of space that are forever beyond our reach. The expansion of space means that our island of visibility is becoming increasingly lonely. Galaxies that we can barely see today will fade from view as cosmic expansion carries them beyond our cosmic horizon. In the far future, beings living in the Milky Way will look up at their night sky and see almost nothing, just the stars of their own galaxy surrounded by an ocean of darkness. The cosmic microwave background will have redshifted out of detectable ranges. The distant galaxies will have vanished beyond the horizon, and the evidence for the Big Bang itself will have been carried away by the expansion of space. This future cosmic loneliness makes our current era seem incredibly precious. We are living during perhaps the only time in cosmic history when intelligent beings can observe the full scope of cosmic evolution, when the evidence for the universe's origins and development remains visible in our telescopes. We are the universe's witnesses during its brief moment of maximum visibility, after which the cosmos will enter an age of increasing isolation and darkness. But our cosmic isolation runs even deeper than the limits of observation. The causal structure of space-time means that we can never influence events beyond our cosmic horizon, nor can they influence us. There might be civilizations out there facing existential challenges that our knowledge could help solve, or they might have insights that could transform our understanding of existence. But the fundamental structure of reality prevents us from ever sharing knowledge, experience, or even acknowledging each other's existence. This isolation extends through time as well as space. The light we see from distant galaxies shows us how they appeared billions of years ago, but we can never know how they appear now. By the time light from our current era reaches those distant realms, our sun may have burned out, our species may have vanished, and Earth itself may be nothing but cosmic dust. We are forever separated from distant regions, not just by space, but by the vast temporal delays that make cosmic communication essentially impossible. The psychological impact of understanding our cosmic isolation can be overwhelming. It challenges our most basic assumptions about connection, communication, and shared experience. We are social beings who find meaning through relationships and shared understanding, yet we live in a universe that seems designed to limit those relationships to an infinitesimally small fraction of all existence. Yet perhaps there's also something beautiful about our cosmic isolation. Like castaways on a desert island, we humans have only each other for company in this vast cosmos. Every conversation, every shared experience, every moment of understanding between people becomes precious against the backdrop of cosmic loneliness. Our small planet, with all its diversity of life and consciousness, represents a rare jewel of connection and complexity in a universe trending toward isolation and simplicity. We are alone together in our cosmic bubble, sharing the remarkable experience of being conscious beings contemplating our own existence in a universe vast beyond comprehension. Perhaps that shared wonder, that collective amazement at finding ourselves aware in such an incredible cosmos, is enough to transform cosmic loneliness into cosmic intimacy, not just with each other, but with the universe itself. As we peer into the deep future of cosmic exploration, we encounter a story that is simultaneously inspiring and heartbreaking, a tale of boundless human ambition running up against the immutable laws of physics that govern our expanding universe. The future of cosmic exploration is shaped not just by the technologies we might develop or the distances we might travel, but by the inexorable expansion of space itself, which acts like a cosmic clock counting down to an age of ultimate isolation. In the relatively near future, the next few million or billion years, cosmic exploration might achieve wonders that would seem magical to us today. Our descendants might develop technologies that allow them to travel at significant fractions of the speed of light, spreading human consciousness and culture throughout our local galactic neighborhood. They might build vast starships that could carry entire civilizations between stars, or develop techniques for uploading consciousness into forms that could survive the rigors of interstellar travel. Within our local group of galaxies, which includes the Milky Way, Andromeda, and several dozen smaller galaxies, there might be opportunities for exploration and expansion that could occupy our species for billions of years. When Andromeda and the Milky Way eventually collide and merge, about 4 billion years from now, the resulting galaxy will offer new realms to explore, new stars to visit, and perhaps entirely new forms of cosmic engineering to attempt. But even these incredible achievements would represent exploration within a tiny corner of the cosmic ocean. The local group itself is gravitationally bound, which means it won't be torn apart by cosmic expansion. But beyond our local cluster, the expansion of space creates barriers that become increasingly difficult to overcome as time progresses. Galaxies that are currently reachable, given enough time and energy, will eventually be carried away by expansion faster than light could travel between us and them. This creates what cosmologists call the cosmic event horizon, a boundary that separates regions of space we can potentially reach from regions that will forever remain beyond our grasp. As time passes, this event horizon shrinks, making fewer and fewer distant galaxies accessible to future explorers. It's as if the universe is slowly closing doors, one by one, on the rooms we might someday visit. The acceleration of cosmic expansion, driven by dark energy, makes this situation even more restrictive. Not only are distant galaxies moving away from us, but the rate at which they're moving away is increasing. This means that galaxies currently beyond our reach are getting farther away ever more rapidly, while galaxies that are currently just barely reachable will soon cross the threshold into permanent inaccessibility. In the far future, trillions of years from now, cosmic exploration will face challenges that seem almost like cosmic horror stories. The expansion of space will have carried most galaxies so far away that they won't even be visible to future astronomers. The cosmic microwave background radiation will have cooled and redshifted to such low temperatures that it becomes undetectable. Future civilizations will inhabit what appears to be a small, isolated galaxy surrounded by infinite empty darkness. These future explorers will face a kind of cosmic claustrophobia that we can barely imagine. While they might achieve incredible mastery over their local galactic environment, perhaps even moving stars, building Dyson spheres around them, or engineering new forms of matter and energy, they will be confined to an island of light in an ocean of darkness that grows ever more vast and empty. Yet even in this seemingly hopeless future, cosmic exploration might find new meanings and new frontiers. As the readily available energy sources of stars begin to burn out, future civilizations might need to become incredibly efficient, learning to extract energy from increasingly exotic sources, either Söderzaubern. They might master the art of harvesting energy from black holes, or discover how to tap into the quantum vacuum itself. The challenge of survival in an increasingly cold and empty universe might drive innovations we can't begin to imagine. Perhaps most intriguingly, future cosmic explorers might turn their attention inward rather than outward. If the external universe becomes inaccessible, perhaps the internal universe, the realm of consciousness, computation, and virtual reality, might become the new frontier. Future beings might create internal worlds of such complexity and richness that they dwarf the physical universe in their scope and beauty. The ultimate irony of cosmic exploration might be that the journey outward through space eventually leads to a journey inward through consciousness. As the physical universe becomes less and less explorable, perhaps the universe of mind and experience becomes more and more the focus of exploration and development. Even there's also the possibility that our current understanding of physics is incomplete, and that future discoveries might reveal new ways to transcend the apparent limitations of cosmic expansion. Even, perhaps faster than light travel will prove possible through manipulation of space-time itself, or through access to higher dimensions that aren't subject to the same expansion as our familiar three-dimensional space. But even if such breakthroughs prove impossible, the future of cosmic exploration remains profound and meaningful. Every journey we take, every new world we discover, every expansion of human presence and consciousness throughout the cosmos adds to the total richness of existence. In a universe trending toward isolation and simplicity, every act of exploration is an act of defiance, a declaration that consciousness and curiosity matter, even in the face of cosmic loneliness. As our journey through cosmic mysteries draws toward its close, we find ourselves confronting questions so fundamental that they seem to exist at the very boundary between physics and philosophy, between the scientific and the sacred. The possibility of escaping the universe, whether literally or metaphorically, forces us to examine the deepest assumptions we make about the nature of existence, consciousness, and our place in the grand scheme of reality. What does it even mean to exist? This question, which might seem absurdly basic, becomes profound when we consider the possibility of transcending our cosmic boundaries. If consciousness could somehow escape the universe, would it still exist in any meaningful sense? Would it still be us in some recognizable way, or would it become something so transformed that the very concept of personal identity dissolves into something larger and stranger? Consider consciousness itself, that mysterious capacity for inner experience that allows you to hear these words, not just as sounds, but as meaningful concepts that create understanding, emotion, and wonder. Consciousness seems intimately connected to the physical processes of brains, which are built from atoms forged in ancient stars, operating according to the laws of physics that govern our universe. Yet consciousness feels like something more than just complex information processing. It has the quality philosophers call qualia, the ineffable something that makes experiences feel like something from the inside. If consciousness could escape the universe, would it take its qualitative nature with it? Or would it discover that qualia themselves are products of our particular cosmic environment, meaningful only within the context of space, time, and the specific physics that govern our reality? Perhaps consciousness beyond the universe would be so alien to our current experience that concepts like thinking, feeling, and being aware would no longer apply. These questions touch on some of the deepest mysteries in philosophy of mind. Is consciousness fundamental to reality itself, existing as a basic feature of the cosmos, like mass or electric charge? Or is it an emergent property that arises only under very specific conditions? The right kind of complexity, the right kind of information processing, the right kind of physical substrate. If consciousness is emergent, then escaping the universe might mean leaving behind the very conditions that make consciousness possible. The relationship between consciousness and information raises equally profound questions. Some theories suggest that consciousness is fundamentally about information integration, the way complex systems bind different types of information into unified experiences. If this is true, then perhaps consciousness could exist in any substrate capable of supporting the right kinds of information processing, regardless of whether that substrate is biological brains, quantum computers, or something entirely beyond our current imagination. But information itself might be more mysterious than we realize. In our universe, information seems to require physical substrates, patterns in matter or energy that can be encoded, transmitted, and decoded. Yet quantum mechanics suggests that information might be more fundamental than the physical processes that carry it. The quantum phenomenon of entanglement creates correlations between distant particles that seem to transcend the classical boundaries of space and time. Perhaps consciousness, if it's fundamentally informational, could transcend cosmic boundaries through some kind of quantum non-locality. The possibility of cosmic escape also forces us to confront questions about the purpose and meaning of existence. If we're trapped in our cosmic bubble, isolated from vast realms of reality that we can never explore or understand, what does this say about the significance of our lives and experiences? Are we cosmic accidents, temporary patterns of complexity that briefly flicker in an indifferent universe before fading back into simplicity? Or are we something more, perhaps the universe's way of becoming conscious of itself, of creating meaning and beauty in what might otherwise be merely a vast collection of particles following mechanical laws? Some philosophers and physicists have suggested that consciousness might be not just a product of the universe, but in some sense its purpose. Perhaps the cosmos evolves complexity, life, and consciousness, not accidentally, but as an inevitable consequence of its deepest nature. In this view, we are not separate from the universe looking outward at it, but the universe looking inward at itself through the eyes of consciousness. If this is true, then every moment of awareness, every experience of beauty or wonder, every act of understanding adds something irreplaceable to the total richness of existence. The question of cosmic escape becomes, in this context, on the question about the ultimate destiny of consciousness itself. If consciousness is indeed fundamental to reality, then perhaps the apparent barriers to cosmic escape are illusions created by our limited perspective. Perhaps consciousness doesn't need to escape the universe, because in some deeper sense, consciousness and universe are not separate things, but different aspects of a single underlying reality, into unreality. This leads us to what might be the most profound question of all. What if the journey toward cosmic escape is not about leaving reality behind, but about discovering what reality truly is? What if the boundaries we perceive between self and universe, between inside and outside, between known and unknown, are constructions of our particular kind of consciousness, rather than fundamental features of existence itself? Perhaps the ultimate cosmic escape is not a journey through space or time, but a transformation of understanding so profound that the very question of escape becomes meaningless. Like a person who suddenly realizes that what they thought was a prison was actually their home. Perhaps we might discover that the universe we thought confined us is actually infinite in dimensions we haven't yet learned to perceive. The deeper questions about existence and consciousness don't offer easy answers, but they do offer something perhaps more valuable. They remind us that mystery itself is a fundamental feature of existence. The universe has given us just enough understanding to recognize how much we don't understand, just enough knowledge to appreciate the vastness of what remains unknown. In a cosmos where consciousness has emerged to contemplate its own existence, where beings made of stellar dust can wonder about escaping the very reality that created them, perhaps the most profound truth is that existence itself is far more strange and wonderful than we can currently comprehend. And so our journey to the edge of everything draws to a gentle close, like a ship returning to harbor after exploring distant seas. We've ventured together through cosmic horizons and quantum possibilities, through the geometry of space-time and the profound loneliness of our expanding universe. Discover not, our journey to the edge of everything draws to a gentle close, like a ship returning to harbor after exploring. Perhaps, in contemplating escape from reality itself, we've discovered something even more precious, the incredible mystery and beauty of being conscious beings in a cosmos that never ceases to amaze. If you're still listening at this point, I'm genuinely impressed by your dedication to cosmic wonder. Please let me know in the comments. Are you still awake? If so, you might be even more fascinated by these mysteries than I am, which is saying quite a lot. Before you drift off to whatever dreams await, I'm curious, do you think consciousness could ever truly escape the universe? Or are we forever bound to the cosmos that created us? Thank you for joining me on this exploration of the impossible. If these gentle wanderings through cosmic mysteries bring you peace, please consider subscribing to help other restless souls find their way to these quiet contemplations of infinity. May your dreams be filled with infinite possibilities, and may you wake refreshed from whatever cosmic journeys your sleeping mind decides to take.